Let's go over the concepts behind problem 8, which deals with free and bound charges and the fields that arise from those charges. Electric flux density, polarization, and electric field intensity. If we have two charges, Q of T and Q, we know from Coulomb's law that the force on Q sub T is our constant, 1 over 4 pi epsilon sub 0, Q sub T times Q over the magnitude of R squared, and the force is along the line between Q and Q sub T. We can define the electric field intensity associated with Q by dividing both sides of our Coulomb's force law by Q sub T. So if we put some charge anywhere, we can find the force on that charge by multiplying it times the electric field intensity at the point of the charge. Faraday introduced the concept of electric flux. So if there's a charge Q, he said there was an electric flux of Q coming from that charge. So if the charge was 3 coulombs, then there would be 3 coulombs of electric flux emanating from that charge, and because of the symmetry, that flux would be spherically symmetric about the charge. So if we enclose this charge Q with a closed surface, so let's use a sphere of radius r. Through that spherical surface, we'll have a total flux of Q flowing through it, and the surface area is 4 pi r squared. So we can define our electric flux density field on the surface of that sphere as Q over 4 pi r squared, and because of the spherical symmetry, we will turn it into a vector pointing in the radial direction. So for any closed surface, if we integrate the electric flux density field over that surface, it's going to be equal to the charge enclosed. So if we look at the electric field intensity for this point charge Q and the electric flux density for that point charge Q, we see that the electric flux density field is equal to epsilon sub 0 times the electric field intensity. So if we replace D in Gauss's law with epsilon sub 0 times E, we can get this alternative form for Gauss's law. Now, up to now, we've been looking at just point charges and free space between the point charges. Let's think about the situation in an insulator, which we also refer to as a dielectric. So these circles represent the atoms in our dielectric, and think of the center of mass of the nucleus at the same position as the center of mass of all the electrons. So you can think of these as being neutral. So now we're going to come in here and we're going to put a charge, like a positive charge, right there. The dielectric is an insulator, so charges can't flow, but all the atoms can get distorted. So the electrons around the nucleus will be pulled towards the positive charge, and the farther away, the less the pull. Now, these charges that form are a little bit different than the charges we've been talking about up to this point. These we're going to refer to as bound charge. And what that means is that the positive and negative part of these atoms can't be completely separated. They're always tied together in this thing we call an electric dipole. So this atom right here we can model as a minus Q sub B and a plus Q sub B. And there's always a minus and a plus together. That's why they're called bound charges. So charges that are not tied up in dipoles we're going to call free charges and associate the electric flux density field as coming from free charges. Those that are bound up in electric dipoles we're going to associate this new field, the polarization, with those bound charges. And the electric field intensity will be due to both free and bound charges. We define the electric flux density field and the electric field intensity as originating on positive charges and terminating on negative charges. We're going to change for the polarization and associate it with starting on negative bound charge and terminating on positive bound charges, hence the minus sign in this equation. So in this equation, let's substitute for Q this expression and for Q sub B this expression. So looking at this equation now, we see that the electric field intensity is equal to the electric flux density field minus the polarization over the permittivity of free space. So with these concepts, we can now go and work problem 8. The only place we can have free charge is on the two metal plates, so electric flux density will emanate from the positive charge on the left plate and not terminate until it hits the negative charge on the right plate. So the electric flux density fields will be the same in the free space region and the dielectric between the plates. Due to the free charges on the two plates, the atoms in the dielectric will form into electric dipoles. So the left side of the dielectric will have negative bound charge and the right side of the dielectric positive bound charge. So we'll have a polarization in the dielectric, and of course, since there's no material in the free space region, there's no polarization. So the electric field is due to free and bound charges. So emanating from the left plate, the positive free charge there will be lines of electric field intensity, but some of those will get terminated by the bound charge on the surface, the left surface of the dielectric, resulting in a lower electric field intensity in the dielectric than the free space region. If we put a Gaussian surface around the left plate, the integral of d dot ds is equal to the charge on that left plate, which is just the charge density on the plate times the plate area, and the integral of d dot ds will just be the plate area times the magnitude of d on this right face. So the magnitude of the electric flux density field is equal to the free charge density on the surface of the left plate. So here's that free charge density on the left plate. So here are the electric flux density fields in the free space and in the dielectric. To find the polarization, we put a Gaussian surface around the left side of the dielectric. So the bound charge enclosed will be the bound surface charge density on the left side of the dielectric times the surface area, and the integral of p dot ds will just be the surface area times the polarization going through the right face. So the polarization is equal to minus the bound surface charge density on the left side of the dielectric. Here's the bound surface charge density on the left side of the dielectric. So the polarization in the dielectric will be 2 times 10 to the minus 9 over 36 pi coulombs per meter squared in the x direction. And of course, in the free space region where there are no electric dipoles, the polarization is 0. So now that we have the electric flux density field and the polarization, we can find the electric field intensity. So in the free space region, the electric field intensity will be 4 volts per meter in the x direction, and in the dielectric it will be 2 volts per meter in the x direction.